Ever type a line of code and think, wow, how did we even get here?
It's a journey, that's for sure.
Yeah, so to everyone listening, get ready. Because in this deep dive, we're going way back, like way back to the beginning of programming languages.
Oh, we're talking punch cards, folks. The whole shebang.
Exactly. From those clunky beginnings to the crazy complex systems we have today. And to guide our little trip through time, we've got excerpts from a programming language timeline.
A regular historical who's who of programming, you could say.
Oh, and of course, no deep dive would be complete without our trusty Wikipedia. This time, we're looking at the programming language entry. Ready to geek out?
Let's do it.
All right, so first things first. Picture this. It's the 1940s. Computers. Think gigantic, expensive, taking up entire rooms. And get this, you program them using punch cards.
Oh, yeah. Talk about tedious debugging. One misplaced punch and you're back to square one.
Oh, I can't even imagine. And that, my friends, is how we got machine language, first-generation stuff. Basically talking to the processor in its own language.
Ones and zeros, all the way, baby. Pretty limiting when you think about it. Not just in what you could, actually make the computer do, but how programmers even approach problems in the first place.
Right, because back then, computers weren't exactly interactive, were they?
Not at all. You ran your program, it did its thing, and that was that. And that, that whole way of working, it really shaped how people thought about interacting with machines.
So how do we go from that to, well, the languages we're using now?
Well, thankfully, we didn't stick with ones and zeros forever. By the 50s, assembly language came along. Still low level, but at least you had symbolic representations of those machine instructions.
So instead of E10100011, you could write something, well, a little closer to English.
You got it. But the big turning point, the real revolution, was the arrival of high-level languages. Mid-1950s. This was huge. We weren't just telling machines what to do anymore. We were expressing, really complex ideas in a way that was closer to how we think.
So that's where Fortran comes in, right?
Exactly. Fortran, short for Formula Translation. 1957, it hit the scene and took off like wildfire. Finally, programmers could write code that looked like actual mathematical formulas, scientific notation, a game changer, especially for folks in physics, engineering, that kind of thing.
And get this, Fortran is still used today.
Oh yeah, still going strong, especially in scientific computing. Talk about a legacy.
It's like the Latin of programming languages, Amazing. But hold on, because we're just getting started. 1958, LISP is born. And this wasn't just a new language, it's a whole new philosophy of programming.
LISP, list processing. This is where we get functional programming, folks. Now, instead of giving the computer a step-by-step to-do list, you define what you want to achieve, and the program figures out how to get it done.
So less about the how and more about the what.
Exactly. This approach recursion functions as first-class citizens. It was powerful stuff, especially for a certain field that was just starting to emerge, artificial intelligence.
Because AI, you're dealing with a lot of, symbolic processing, patterns, uncertainty.
Right. Areas where this kind of functional programming really shines.
The LISP's influence, it went way beyond just writing code. It pushed the boundaries of what computers could even do.
Absolutely. And as computers themselves changed, getting smaller, more accessible, well, the languages had to keep up, didn't they? Which brings us to the 70s and 80s, the age of the microprocessor.
Yeah, the microprocessor, big change. It's like suddenly you don't need a room-sized computer to do amazing things.
Right. Computing power for the masses. I love it. So how'd programming languages handle this shift? Everything's getting smaller faster.
Well, that's when you see languages like C really taking off. C gave programmers incredible control, down to the metal. Perfect for things like operating systems, embedded systems, that sort of thing.
But that level of control, that must come with, a certain level of risk, too, right?
Oh, absolutely. It's powerful, but you got to know what you're doing. C, it doesn't hold your hand. Memory allocation, deallocation, it's all on you.
Yikes. And it's no safety net if you accidentally, step into the wrong memory address. You're on your own, kid. Which is why, of course, languages kept evolving.
Yeah.
New ways to manage all that complexity. And that's where object-oriented programming pops up.
OP.
Yeah.
Right. The Lego analogy, building programs out of reusable blocks.
You got it. Instead of these huge, long, sequential programs, you're creating objects, little bundles of data and actions.
So, instead of building a car from scratch every time, you've got engines, wheels, transmissions all ready to go.
Exactly. And you can even create variations. Sports car engine, truck engine, all based on that same blueprint. It made code so much more organized, reusable, easier to keep track of.
Makes sense. From handcrafted to mass production almost. But before we jump ahead too far, the 1980s, that's also when Japan launched that fifth-generation computer systems project. Ambitious stuff, from what I remember.
Oh, yeah, definitely. They were aiming to build computers that could, well, almost think like humans. Massive parallel processing, logic programming. It was a whole thing.
And wasn't their plan to use Prolog, that logic programming language?
Right. The idea was, instead of telling the computer exactly how to solve a problem step by step, you'd describe the problem and the desired outcome. Let the computer figure out the logic. And while it didn't quite achieve world
It
domination.
didn't turn into Terminator,
Yeah.
thankfully.
Not quite, but even though it might be considered a failure in some ways, it really pushed computer science in new directions, got people thinking differently.
Proof that not every dead end is a total dead end, right?
Exactly. Sometimes those big swings, even if they miss, they inspire breakthroughs in other areas. And speaking of breakthroughs, the 90s. The internet arrives. Everything changes. Again.
Right. And suddenly, programming's not just about what's happening on one computer. It's about connecting the entire world. I mean,
Yeah.
before the internet, software was kind of, well, isolated, right? Stuck on one computer. But connect everything together. You need a whole new way of thinking about programming.
Yeah, and it's not even just connecting things. It's about software that can, keep up with the internet, change fast. Imagine if you had to, wait for a software update every time a website updated.
Ugh, Stone Age. So how'd programming languages, how'd they adapt? Java, that was a big one, right?
Huge. Java, it was designed to run anywhere. You write the code once, and boom, it can run on any machine that's got that Java virtual machine thingamajig. Didn't matter what operating system or anything.
Like a universal translator for computers. That's cool.
Exactly. And that portability plus Java security features made it the language for web development, especially back in the late 90s, early 2000s. But something else was happening too. All these scripting languages start popping up. Python, JavaScript, PHP, Ruby.
Right. Those were everywhere. Websites, web apps.
Mm-hmm.
What made them such a good fit for the web, though?
So unlike Java, where you have to compile the code first, these scripting languages, they were interpreted, run on the fly. Way more flexible for web development. Things change fast, you need to adapt quickly. Plus, they were just generally easier to pick up, which meant more people could get into programming.
Lower barrier to entry.
Yeah.
I like it. So much going on in the 90s. Did things ever slow down?
Not really. The early internet, you saw these general purpose languages trying to do it all. But then in the 2000s, things shifted again. Specialization became the name of the game.
Instead of general practitioner, you've got a heart surgeon. I like it.
Exactly. Take Rust, for example. Super focused on safety, making sure your code doesn't crash and burn. Perfect for things where reliability is, mission critical.
And Go. That came out of Google, right? Handling all those users, all that data.
Yeah. Concurrency, efficiency, all that good stuff. You need a language that can juggle a million things at once. That's Go.
It's funny, when you think about it, the way programming languages have evolved, it's like a mirror of how technology itself has changed. But what about the visual side of programming, like Scratch, or even game engines that use visual scripting?
Great point. Visual programming, that's a whole other branch in how we interact with computers. Not just text anymore. It's drag and drop. It's visual logic. Really opens things up, especially for beginners or fields like game design, education.
It's like instead of writing out sheet music, you're just playing the instrument. Different ways of expressing the same ideas. So as we wrap up our little trip down programming language memory lane, what's the big takeaway here?
This journey, it's not over. Not even close. The problems change, the technology changes, and the languages, they have to keep up. What's next? Who knows? Maybe we'll see a comeback for those general purpose languages. Maybe specialization keeps going. Maybe we'll ditch text altogether and just talk to computers.
Now that's something I'd love to see. It's like you said, the world of programming is dynamic, it's always changing. So whether you're a coding guru or just starting out, remember, keep exploring, keep asking what if. You never know. You might just invent the next Fortran, the next Python. Change how we interact with technology forever. And hey, thanks for joining us for this deep dive. It's been a blast.